simulating damage, right? And so what we discussed was, if you take a small piece of element, then so if you take a small piece of volume of the material which you want to simulate, so where you want to simulate the damage, there after some amount of deformation, voids will nucleate. Okay, so this is the mechanism for ductile damage, not for brittle damage. Okay, so voids will nucleate and then they will grow, then they will coalesce. And how do we incorporate that in finite element analysis or numerical analysis? By defining a damage parameter. Okay, and that damage parameter will enhance the stress. Okay, so how will you proceed? You will proceed by applying an increment of displacement or increment in force. So any of these two can be the boundary conditions. Based on that, you will calculate what? So you will have initial, so previous value of the displacement, right? And then you are applying this much amount of increment to that. So your new displacement will be plus delta U. Right? When you start like this with an approximation based on the previous step, that is known as explicit analysis. And when you predict the solution for the current iteration at the end, so you do all the calculation and then at the end you write I plus 1 is equal to current value plus whatever delta U you have converged for, and then you update that. So that is implicit, but we will discuss it later. So fine, so you have some amount of delta U. For that delta U, you will calculate strain. Okay, so you will calculate B matrix and you will calculate strain, and then from that you will calculate stress, and then from that you will calculate stiffness. This is for 2D. You will have thickness, you will have and if you have 3D, you will have one more integration, thickness will go away and you will have another variable there. Okay, and then you will assemble all the stiffness matrix for all the elements, and then you will solve this equation. This is global stiffness matrix, this is global displacement matrix, which is just have one column, and then you have forces. If you have external forces, then external forces. If you have only internal forces, then you have internal forces, whatever the forces are. Okay, and so when you calculate stress, before that you have calculated strain, and from this strain tensor the value of damage will be defined. Okay, so amount of plastic strain will define. So I told you yesterday that you have to decide that when the damage starts occurring. So when this parameter will have a value greater than 0, that will be your initiation of damage. Okay, so that will be decided, that cannot be decided by stress in this case, in ductile damage. So if you want to divide the damage mechanics into two cases, then broadly two cases are strain based and stress based. Okay, so ductile failure, ductile damage is described based on strain, and brittle fracture is described based on stress, because you have not significant amount of strain in case of brittle fracture. Okay, so plastic strain is very limited in many of the brittle materials, so you cannot have a strain based criteria. Okay, so in this case, some strain parameter you can take a combination of, so equivalent plastic strain, that can be a parameter which can describe that when that crosses a critical value, you have some value of omega. Okay, so initiation, and after initiation you will have a kinetics, how this damage develops, how omega increases. So omega is starting with a value of 0 and it goes to a value of omega f which is less than 1. Okay, you don't really have to go to 1, but what happens in between omega I and omega f? It's not linear. It can be linear, it can be any other way. So you need to know the kinetics of damage. Okay, so in a tensile specimen, voids are generated and then they grow and then they coalesce. How does that happen? And when we do this, we are really not going to simulate voids because we are not doing that. In finite element analysis, by using this formulation, do you see anywhere there is any info of the void location? We are just defining a parameter which is enhancing the stress, and by doing that it is degrading the stiffness. That's it. Omega really is not physically present anywhere. So you don't have these voids in physicality in finite element analysis. They really don't exist. Okay? So when you cut across a plane, then you are saying that certain area must have been decreased because of the presence of these voids, right? And that area decrement you are taking as omega. Okay? And then you are correcting that area by 1 minus omega, and you are correcting or updating the stress value. This is what you are doing, right? So this is equalizing this to a smaller area element which has no void in it, isn't it? So because of voids, the real area is now decreased by the omega parameter. So if I define another element which has no void in it and the height is same, but this dimension has decreased, thickness is same and no void in it, and this has an area of K which is equal to A0 into 1 minus omega. So this is what I am doing, right? I am correcting the area by the amount of damage parameter, and I am really not simulating any void in the finite element analysis. There is no information of location, there is no interface of void with the element. No new elements are being generated. If you have to simulate void, really, then you will have to remesh in every increment because you are creating new surface. That you are not doing here. Okay? So this is called continuum damage mechanics because you are not breaking the continuum really. In reality, it becomes discontinuous. Okay? You have voids which has surface and the matrix is not there. So there is a discontinuity. But that you are not simulating. You are taking care of that by using a damage parameter. So this becomes continuum damage mechanics. And our yielding criteria has also not changed. Our yielding criteria is still based on von Mises. You can take Tresca. But that yielding criteria is not updated or enhanced by the damage parameter. So omega is not influencing the formula used for finding out whether or not the thing has yielded. right? So sigma 1 minus sigma 2 whole square and some like that. That thing is not changing. What is changing is those sigma 1, sigma 2 and sigma 3 are changing because of omega. Okay? There can be another way where you also update the stress and you also change the yielding criteria. Okay? So if you model a tensile specimen using this formulation, then only you can simulate the real stress strain curve, whatever is the shape of this. Okay, even though true stress should be going up always, but the reality is that the sample will neck, right? If you don't have damage in your formulation, if you just have quadrilateral elements with elasticity and plasticity, and then you run the code, and then you apply whatever displacement you want to apply, your sample will keep on elongating till eternity. Well, not till eternity, because the convergence will fail. Okay, so there will be no solution after some time, and your code will just get aborted. Okay, but no necking will happen. There will be elastic strain, there will be plastic strain, that's it. It will just get elongated. So this tensile sample will elongate with a Poisson's ratio of 1 by 3 initially, if that is that. And after that, it will elongate uniformly with a Poisson's ratio of 1 by 2. And it will always be uniform. Okay? So unless you create damage, only then you can simulate necking. And how do you simulate necking? Because damage also can develop anywhere, but damage will be developing based on the criteria of your definition of damage initiation. So damage initiation will be happening where your plastic strain, equivalent plastic strain, is maximum. Suppose that's the criteria. So your maximum shear stress is going to be like this for uniaxial condition, 45 degree. Sigma 1 is maximum, sigma 3 is minimum. So between sigma 1 and sigma 3, you are going to have maximum shear stress. Along that direction, you are probably going to have maximum shear strain. So maximum equivalent plastic strain. And the damage will initiate on these regions. And this region is not rectangular, it's a cylindrical specimen. So you have a conical shape where damage will initiate. And a lot of damage will initiate here. And wherever you have damage, you have higher stresses. That causes higher strain, that causes higher damage, that causes higher stress again, that causes higher strain again, that causes damage. So it will be a loop, and you will have more and more damage there, more and more stress there. So more deformation will be here in comparison to other places. So then it will start necking. So this non-uniformity of different amount of strain can only be introduced when you have a damage parameter. Okay? कुछ समझ में आ रहा है? नहीं आ रहा है? So ये तो simulation है. So this is what you are modeling, and you can have a look at these pictures where you can see what really happens. So these are at different magnification. And ये क्या गया?
सर इलेक्ट्रिसिटी कट है.
पावर कट हो गया. ठीक है, जब आएगा तब आएगा. So so a lot of research happened on and has happened and is also happening and will be happening in the future. It's not going to stop. And a lot of research has happened on damage, how, and especially on ductile damage, and how the voids they develop, nucleate, where they nucleate, what are the sizes, are they really spherical, do they really coalesce, what contributes to the growth of the ductile, so the voids, okay. And there is, okay, so now we are here. So what do you see? Nothing.
initiation.
हाँ अब क्या हो गया इसको? आज तुम लोग लकी हो, ये सब वेरी लकी। क्या हो गया? ये आके क्यों चला गया? Shouldn't have broken that. Okay, so nucleation of void has been found in research to be triggered by the shear stresses. Okay, and shear stress is needed for dislocation movement also. Shear stress is also needed for void generation. Why void will generate? Because you will have somewhere some strain incompatibility where a part of the matrix will not be able to stretch as much as the other part. Okay, so if you have inclusion, on this side you have oxide or carbide, and other side you have steel. So steel is going to deform more, carbides are not going to deform that much, oxides are not going to deform that much. Okay, so on this point, for the same amount of stress, you will be having two different amount of strains because of the elastic modulus of the oxide on one side and elastic modulus of the steel on the other side. Just imagining pure elasticity. So that point cannot have two different types of stretching. So it is better that it separates. And all these weak points where you have this kind of phenomenon, they will separate and they will create a void. What will happen before going to that point is that oxide will break, not at the interface, from within. So you have seen graphite in your pencils, that will not hold for long, it will break. It breaks, so there is already a separation. Okay, so holding the amount of strain which matrix is going through is really possible if you have a broken discontinuity, so it can just stretch, so it acts like a void. Okay, so voids nucleate because of the shear stresses, which can be represented by equivalent stress, von Mises stress. Okay, so for the sake of non-dimensionality, it is always good to normalize it. Okay, and then you will have growth of these voids, and these void growth are dependent on the hydrostatic stress component because of the volumetric strain. Okay, so then I can normalize that also, and let us say I take a function here, and the amount of void which is forming in every stage will be decreasing the yielding, because if the amount of force which was needed to yield at, let us say, ith iteration, you don't need that much amount of force to yield in the next point when you have more void, because the load bearing capacity of that representative element has decreased. Is it making any sense? Okay, so I must take care of how much void volume fraction is forming in every step, how much growth is happening, how much nucleation of void is happening. Okay, so this will be defining my new yield point. And in this case, apart from hardening, the curve will go down. So you can also simulate softening because the new yield points are lower than the previous one. Okay? So this could be another way of defining yield point in comparison to what we had, von Mises criteria. Okay? So in this case also we are calculating von Mises, but we are not saying that when sigma equivalent minus sigma naught is equal to tolerance, we cross or greater than equal to tolerance, we go in the plastic domain. We are not saying that. We are saying that this must be greater than 0, greater than equal to 0. Then plasticity will happen. Okay?
Sorry, have you tried this? Curtains?
No.
Okay.
Should I try?
Give it a try if it is
Okay, I'll try.
doing the serving the purpose or not.
ये तो इतना ही तक है इसके आगे जा नहीं सकता है
अच्छा नहीं
नहीं यहाँ पे ब्लॉक है
ठीक है चलो मैं बोल नहीं मैं वो ट्राई लिया है ना
अच्छा okay, so this where you have a different yield function which is dependent on damage parameter. And what is the damage parameter here? What is the damage parameter here? F. What is F?
Damage parameter.
Yes. F is void volume fraction. Void volume normalized by the total volume. Okay. So then you know that this is very specific to ductile damage. Okay. Whereas the previous one, where you had omega, that can also be used for brittle fracture. Okay, that is very generic in nature. So that formulation you can use for a combination of ductile and brittle fracture. Because there you just need to change the kinetics from where omega is equal to 0 to omega is equal to F. What path that follows will be describing your ductile behavior or brittle behavior. Okay, and how do you get the kinetics of omega? That you get by doing experiments. Okay, but it's not that easy. So you can do experiments in different ways, and you can. So when you do tensile testing, what people do is they stretch it and they don't go until failure. They don't break it. Okay? And what they do is, so you can do in two ways. One is that you take a tensile sample and stretch it to different values of strain, 0.3 and so on. So you take 10 different tensile specimens. One you stretch it at 0.1 and stop the test. Second 0.2, stop the test, and so on. Okay? And then what you do, you dissect it at the center and you look at the voids. Okay? So by measuring the area here, how much area reduction has happened, you can find out what is the value of strain there. Right? And for that amount of strain, how much void volume fraction you had, that you can see under scanning electron microscope. Okay? And by doing it for 10, 20 specimens, you will have kinetics of strain versus void volume fraction. So you can plot F versus epsilon. And this should be the kinetics of omega. Instead of doing 10, 20 specimens, you can also do it in one specimen. Okay? So you stop it just before failure or as soon as the necking develops. Okay? And then instead of cutting like this, you cut it like this along the axis, and look at under scanning electron microscope, and you will find different amount of void volume fraction here, 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 and so on. And in one specimen you can also measure how much area reduction has happened at these points, and from one specimen you can calculate strain versus void volume fraction. The difference will be that if you take 20 specimens, then you will have, those are 20 different specimens. So all of them has different heterogeneity in it. Different distributions of carbide, different distributions of secondary phase particles, grain boundaries, and other things. One specimen is not going to disturb you that much, but it is also not going to give you that much statistics. So the best way would be to take 3 samples, do the axial sectioning, look at it under scanning electron microscope, find out epsilon versus Vf, and average it out for 3 specimens, and then you use that for omega kinetics. The error will come because of approximation of 3D entities in 2D. The things which you will be looking at under scanning electron microscope will be area, and voids are a 3-dimensional things. Okay. So if you have rolled, and even if you have not rolled, you are actually deforming it in one direction. Okay. So the voids are going to stretch in one direction, right? If it has rolling, then you will have voids which will be oriented in a different direction. And when you do the serial sectioning, you don't really expect. So you are measuring this and you are not measuring this. So you are imagining this. You are imagining that to be a sphere and calculating the void volume fraction. So that error will come. What to do about it? So there can be another way of finding out what is going on inside the material. What could be the other way? You will again have same error. Transmission में क्या पूरा कैसे दिखेगा? So what could be the other way? ये तो जल रहा है, फिर आप क्यों नहीं रहते? ओह, उधर से तो कहीं बंद नहीं हो गया?
चल गया.
बोलो, what could be the other way? So what is this? What are you looking at? Can you? Crack initiation? No. No. It's a sample which already had a crack. Okay, so it was a fracture sample. So you already had a notch and then a crack propagated. Okay, and a small piece was, so this has propagated, so it has opened up. And this is an exaggerated view, it really doesn't look like this. And then you take a small piece here, polish it, etch it, then look at it. You can also see without polishing, and you will see the crack profile. But if you polish and etch it, then you will also see the grains and boundaries and carbides. Okay? So what you see here, these are the voids. Okay? You have a lot of voids here. And the expanded view is here, so you see a lot of voids has come. And these are micro cracks. Okay. So you see, this is a bigger crack which has formed because of joining of 2 small cracks. Okay, 2 small micro cracks. So you have micro crack there, there, there. These are not voids. They form from the secondary phase only. But micro cracks contributes to brittle fracture and void contributes to ductile fracture. So we'll discuss about micro cracks later. But I don't know if you can really see. Well, here it is visible, but on the projector it is not. So can you see these lines? Can you see some features there or here? Do you see something? You have very small white things along certain in a pattern. Okay, so those are M23C6 carbides. Okay, those are C23C6 carbides. Sorry, CR23C6 carbides. Okay, and this microstructure is of a tempered martensite structure, and the pattern which you see is the grain boundary of pre-austenite. So it was previously austenite, then it was quenched, it became martensite, and then you temper it. So although the martensite will lose its tetragonality, carbon will go out, but it will not look like ferrite. The microstructure will look like tempered martensite only. So you will still have lath features if the martensite was lath, plate features if it was plate needle, and all those things. Okay. So you have different types of carbides. So this is generally known as M23C6, and then you have MC, M2C, M4C, and different elements form different types of carbide. And vanadium and tantalum, they form this type of carbide. And these carbides are even smaller than this one, and this you will find on the, they will not form at the grain boundary, pre-austenitic grain boundary. They will form at the lath interface and in the size of nanometer because of the history of it, because of the kind of heat treatment given to this particular steel. Okay, so you have a lot of distribution of secondary phase. One way to look at it is that we shouldn't have secondary phases, but then you will not have strengthening. We have seen precipitation hardening. So secondary phases will give you a lot of strengthening, and these carbides, they hold the grain boundary from grain boundary movement when you have high temperature deformation. So grain boundary sliding happens in creep. Okay, and if you have carbides which are sitting at the grain boundary, then they will not allow this movement. So they pin the grain boundary. Okay, so you need these kind of things. So one way to define such damage was updating the yield function by counting for the nucleation of void which is happening and the current status of void volume fraction, subtraction of that from the yield function, and keep on updating the yield function. So in that case, what will happen? On your sigma 1, sigma 2, sigma 3 diagram, the von Mises ellipse which you had, in this case, this ellipse will be decreasing in radius with damage increment. So when strain hardening happens, so for the domain where you have strain hardening happening and omega is equal to 0, for a very long period of time omega will be 0. So in that case this radius will keep on increasing, and when omega starts developing, then it starts decreasing. So then softening happens. Okay, so this kinetics can also be used probably for simulating the softening which happens in polymers, because the formulation is not worried about whether you have void. Omega based formulation is not worried about whether you have void in it or if you have the entangled chains of molecules which are opening up. It is just taking care of the decrement in elastic modulus which is happening. Okay, so you can use this trick to simulate polymer also. So if we focus on just damage kinetics, so evolution of damage in metallic materials, ductile materials, what could be the other way of measuring how much damage is developing in the system? कोई और तरीका है काट के देखने के बजाय? So whatever we see in space, for example, we don't really see it. People do a lot of data analysis, right? So can there be an indirect way of finding out what is happening inside the material? बोलो, कुछ और तरीका हो सकता है? फ्रैक्चर होने के बाद तो टूट जाएगा। डैमेज देखना है मेरे को कि डैमेज कब इनिशिएट हुआ और कितना डेवलप हुआ, वो देखना है। देखना मतलब अमाउंट जानना है। कैसे कर सकते हैं? सरफेस
सरफेस को देख के,
सरफेस को देख के सारा वॉइड तो सरफेस पे नहीं आएगा।
कैसे होता है फिर सर?
नहीं, सरफेस पे स्ट्रेस नहीं हो सकता है। सो स्ट्रेस goes to zero. It develops inside and it goes to zero at the surface. So surface will be the last thing where damage will initiate in monotonic loading. In fatigue, it will develop at the surface first. But in fatigue, you will not see damage. You will not see voids. तो क्या तरीका हो सकता है, कुछ बताओ? What if I pass electric current with the in the tensile specimen? तो मेटालिक है, कंडक्टर है, तो उसका कुछ रेजिस्टेंस होगा। तो जब डैमेज इनिशिएट होगा तो क्या होगा? उसमें चेंज क्यों आएगा? ठीक, so the same concept goes and resistivity will change, right? So because the resistivity will change, you can measure the voltage drop, or you can also, so by voltage drop you can measure what is the resistance change, resistivity change, and resistivity will directly give you a measurement of damage which is happening, right? Whether or not it will give you any signature, so you can write, so resistivity can be written as, or resistance can be written as R into rho into L by A, right? So this is L, and suppose if the thickness is 1, then this is A, right? So what will happen at plasticity? Do you think resistivity can also give you a signature of yielding? Or not? क्यों, कैसे?
कुछ तो चेंज आएगा मटेरियल।
अरे कुछ का बात तो होता तो मैं लिखता ही क्यों? तो कुछ से थोड़ी होता है, कुछ होगा तो कुछ होगा। एरिया तो इलास्टिसिटी के टाइम पे भी चेंज हो रहा है। अरे वो तो इलास्टिक डिफॉर्मेशन में भी एरिया चेंज हो रहा है, तो कैसे पता चलेगा यील्डिंग का? रेजिस्टिविटी, let us say, is decreasing, okay? So then after damage it decreases and changes the slope. So then you know कि यहाँ पे change हुआ slope, यहाँ से damage initiate हुआ होगा। Will you have a change in slope if it goes from elastic to plastic deformation? क्यों होगा? कोई फायदा है क्वेश्चन पूछ के? तुम क्वेश्चन के जवाब क्वेश्चन कैसे हो सकता है? So change in A can be written as change in diameter, right? And change in diameter per unit change in length is represented by Poisson's ratio. Poisson's ratio will change when plasticity begins, right? Whatever is the value, 0.3, 0.45, it will change to 0.5 when plastic deformation happens. It is a different question that plasticity really doesn't, there is no point where plasticity really starts happening. But an average plastic deformation happens. So there could be a point where you will have a change in slope when yielding happens. Okay? So this could be another way of measuring how much damage is happening. And there are other ways also to measure the amount of damage, and all those ways have their own errors associated with them. With those errors, we have to deal, and we have to take the kinetics of omega. Okay, so if you do that experiment or resistivity experiment, you find out the kinetics of change of resistivity, relate it to omega, put it in the formula, simulate it for your tensile specimen, and then you match the load displacement curve for your experiment and the finite element analysis. It will not match. So then you need to change a little bit, because there are errors in your measurement. So it will never exactly match. Okay, so then you need to tweak those parameters, the damage parameters, the kinetics of damage, a little bit up, down, the values, and then you should be able to good to go. Okay. So, how many of you remember Abrami's equation? Have you heard of Abrami's equation?
Yes, sir.
Do you remember it? नहीं सीधा तुम्हारा तो कॉन्सेप्ट ही क्लियर है ना. So if for, let us say, for an amount of tau time, you have some nucleus which is forming. Okay, so the amount of total nucleation you can write as V into nucleation rate into d tau. N dot is the nucleation rate for the amount of d tau you are nucleating. V is the total volume, so nucleation rate is per unit volume, so you multiply with the volume, so you have the total volume of the void which has nucleated, right? And then they will grow, right? So the total volume which is coming up will be what? So now you can't look at here, you have to go to a time t, because growth will only happen when something has nucleated. So before time tau, there was no nucleus, so nothing can grow. In the time d tau, you have certain nuclei form, so they will grow, and they will grow for the time t minus tau. For that period of time only they will grow. Okay? So if the growth rate is defined as dr by dt, where you assume your voids precipitates to be spherical, then the volume change can be written as is proportional to del r cube. So that will be proportional to the growth rate into dt cube, right? So this will be equal to volume. So but you have the growth volume which is g dot into time minus tau whole cube, and then you have to multiply with this, because because when the growth is happening, nucleation is happening simultaneously. Okay, it cannot stop. So you will have v n dot d tau, and then you integrate this, and then you get a volume, and that volume is not taking care of the things. So if these are growing, new nucleus are also forming, new nuclei are also forming, right? and these nuclei can also form within the grown area. If the parent phase was alpha and the new phase is beta, then no equation in that is suggesting that beta cannot nucleate inside beta. That we have not taken care of, right? And then these two can also grow inside each other. That also we are not stopping. From our equation, in our assumption, there is no mathematical expression which says that for the amount of t minus tau, nucleation cannot happen in already transformed regions. We are allowing that, right? We are also allowing the growth to happen in already transformed regions. So that's an erroneous volume. That's an incorrect volume, right? And this incorrect volume, so the really transforming region per unit erroneously transforming region must be proportional to the untransformed volume. And this is how you correct and find out the final Avramies equation. Have you read this? इसको पढ़ाया नहीं गया पहले? क्या?
ऑनलाइन में
हाँ?
Avrami question like e to the power कुछ था उसमें.
हाँ e to the power आएगा when you do the integration. You have to do the integration of this. Then you have to write b beta there. Okay. So not b beta there. So you have to put there this thing there. Then you integrate these two, and then you will have the final expression will be db beta. So you will have v beta by b is equal to 1 minus exponential of minus gamma into t to the power 4. This will be your final expression after doing the integration. So this is a mathematical model, right? And this mathematical model is telling you that in a parent phase, if a beta phase is precipitating, it can be a complete transformation from alpha to beta, where you have final transformed volume is equal to 100%. Okay, so that also can happen when austenite changes completely to ferrite. Or you can also have a transformation where alpha transforms to alpha plus some precipitates. And in that case, V beta by B will be representing the transformed volume of Fe3C because alpha is untransformed. So in that case, it will not go to 100%. Okay. So I will leave this session with one question which you should think about, is that can we apply this in case of void nucleation and growth? Okay, think about it.